In this video, we are going to look at the zeros of a polynomial function. We're going to evaluate a polynomial using the remainder theorem. We're going to use the factor theorem to solve a polynomial equation and to help us factor. We're going to use the rational zeros theorem to help us find potential and actual rational zeros, if they have any. We're going to find the zeros of the polynomial function. We're going to use the linear factorization theorem to find the polynomials with the given zeros, and then we're going to solve some real-world applications of polynomial equations. And I do want to mention Descartes' rule of sign because that's also in this section. So we're going to use synthetic division to find the quotient and the remainder. So with synthetic division, remember that I take the opposite of what I see here, because what I'm doing is I'm doing x is equal to -2, therefore I put a -2 in there. And then I take all the coefficients off of this, and if it's missing anything, make sure I put in a 0. So a coefficient of 1, I don't have an x squared, so it'll be a 0. A coefficient of the x, it's a -3, and then the constant. The 1 drops, -2 multiplied by 1 is -2. Those add together vertically. So -2 multiplied by -2 is a +4, so those add, so that gives me 1. And then -2 multiplied by -1, or -2 multiplied by 1 is a -2, so my remainder is 0. So my quotient, my q of x, is x squared minus 2x plus 1. I'm going to do the same thing here, and when I solve for x here, I'm going to get x is equal to a -1/3. So I will have a -1/3 here, 6, -1, 5, and 2. I'm not missing any of the terms. 6 drops down. 6 multiplied by -1/3 is a -2. And then -1 plus a -2 is a -3, so -3. -3 multiplied by -1/3 is a +1. 5 plus 1 is 6. 6 multiplied by a -1/3 is -2, so my remainder is also 0. So my quotient here is going to be 6x squared minus 3x plus 6 with my remainder of 0. I should say up here my remainder is also 0. Okay. So how is the range of a polynomial function related to the degree of the polynomial? Well, we know when we look at our parent or toolkit of functions that when I have x to the n and n is odd, then I have no restricted range. I'm going to go from -infinity to infinity. However, when I have x to the n is even, then I also have to take into account when the leading coefficient, so we'll assume a sub n initially is greater than 0. When that happens, then my range is going to start at my absolute min, and I will have an absolute min. So I have an absolute minimum value all the way to infinity. If I have x to the n is even, and a sub n is less than 0, then I'm going to have an absolute maxima, which means my range is going to go from -infinity to the absolute, and I will have an absolute max. Is it possible for a polynomial function to have no y-intercept? And the answer is no, unless if the polynomial function represents an application, a real-world application, and it makes no sense for it to have a y-intercept, then no, it won't have one. But if that's not the case, which is very, very rarely, then every single polynomial function will be guaranteed a y-intercept. They're not guaranteed x-intercepts because if we think about our parent function or toolkit of functions x squared, if we do a transformation, so I have f of x is equal to x squared plus 2, then we know that this is our parent function that has been moved up 2, and we have no y-intercept, or excuse me, x-intercept. So yeah, it's totally possible to have no x-intercepts. It's not possible, with the exception of applications, and certain applications, to have no y-intercepts. Explain why the values of a function must be all positive or all negative consecutive zeros. Actually, that's not true. So I can think of a polynomial easily. Let's do x squared minus x minus 12. Here's my function. If I factor this, I have x minus 4 and I have x plus 3. So my zeros are negative 3 comma 4. So they're consecutive, but they're not all positive and they're both not negative. So it's not true that a function has all positive or all negative consecutive zeros. So if you had an absolute value function, that's still not necessarily true if we have an absolute value function that has been moved down with a transformation of graph. In synthetic division, why is the degree of a quotient 1 less than the dividend? Well, if we take a look at our example up here, when I did, we'll look at the easier one without fractions, because I know everyone doesn't like fractions. When I did this negative 2 and I divided it into this synthetic division, I had to do a linear. When I'm doing a linear division, so this is a linear x plus 2 into a polynomial and synthetic, you are always going down 1 degree. In fact, let me show you what it looks like if I have something like this, x cubed plus 3x squared plus x plus 5. If I'm dividing by x here, where this is x plus 0, I'm not going to do synthetic division because it isn't necessary. What I can do is just rewrite this as x to the third over x plus 3x squared over x plus x over x plus 5 over x. And you can see the resulting expression would have been x squared, so you can see I've dropped a power, plus 3x plus 1 plus 5 over x. These expressions where I have x cubed plus 3x squared plus x plus 5 over x is equivalent to x squared plus 3x plus 1 plus 5 over x, and you can see I have dropped a power. Now, I just did this to make it easy to show why, without going into great detail, why we end up dropping a power. In this section, we're going to use two big theorems, the remainder and the factor theorem. And what the remainder theorem says is if I take x minus k and I divide it into some polynomial, I'm going to get some remainder. And I can find that remainder by doing synthetic or long division, but I can also find it by just putting that k value into the function. The factor theorem says, hey, and you know what, if I did that, if the answer is 0, then x minus k is a factor. So if we go back up to our example right here, we're going to go back up to this lovely example. If I put in my polynomial, or if I put in my polynomial function, if my original function is x cubed minus 3x plus 2, and my k here, the thing that I'm going to be checking, is negative 2. If I do f of negative 2, I get negative 2 raised to the third minus 3 multiplied by negative 2 plus 2. This is negative 8 plus 6 plus 2, which is 0. This is my remainder, and this is also my remainder. And that tells me, because my remainder here is 0, that tells me that x plus 2 is a factor of f of x. That's what the factor remainder theorem says. Okay. So we're going to use the factor theorem to determine if the given linear expression is a factor of the polynomial. I'm not going to use synthetic division on this. I'm just going to say here's my function f of x is equal to x to the third minus 8. So f of negative 2 is negative 2 raised to the third minus 8. This gives me negative 8 minus 8, which is negative 16. This is not equal to 0, so not a factor. Let's do the next one. I have f of x is equal to x cubed plus 6x squared minus 25x plus 18. I'm going to do f of negative 9. So I have negative 9 cubed plus 6 multiplied by negative 9 squared minus 25 multiplied by negative 9 plus 18. Oh, I can't do this one in my head. So get my calculator out. And I'm going to get negative 9 cubed. I'm just putting it in my calculator. I'm just letting you all be a part of it as I put it in my calculator. 6 multiplied by negative 9 squared. And then minus 25 multiplied by negative 9. And then plus 18. Ooh, this equals 0. That tells me that this is a factor. Let's do the next one. So I'm going to have f of x is equal to x to the 7th minus x to the 6th plus x to the 5th minus x to the 4th plus 2. F of negative 1. Negative 1 to the 7th minus negative 1 to the 6th plus negative 1 raised to the 5th power minus negative 1 raised to the 4th power plus 2. Get negative 7 minus 1 minus 1, actually negative 1 minus 1 minus 1, minus 1 plus 2. I end up with negative 2, not a factor. Not a factor. And that's because this is not equal to 0. All right. Use any method you like to determine whether the numbers given are the zeros of the polynomial. So for the first one, I'm just going to put the numbers in and see what happens. So I'm going to do f of negative 2. So I have negative 2 to the 3rd minus 6 multiplied by negative 2 plus 11 multiplied by negative 2 minus 6. And I end up with negative 24. So not a factor. Actually, it's not a 0, which means x plus 2 is not a factor. Not a factor. Now I'm going to do f of 1, which is 1 cubed minus 6 multiplied by 1 plus 11 multiplied by 1 minus 6. And I end up with 1 minus 6 is negative 5 plus 11, which is positive 6. Negative 6, this is 0. So x minus 1 is a factor. I'm going to do f of 3. So I'm going to have 3 cubed minus 6x 3 squared plus 11 multiplied by 3 minus 6. This is 0. That tells me that x minus 3 is a factor. All right. For the next one, let's do synthetic division. So we have negative 3 goes inside that little house. I have 1, negative 1, negative 1/9, and 1/9. 1 drops. I get negative 3. This gives me negative 4. This gives me positive 12. So this gives me positive 11 over 8/9. And then I multiply that by 3. I can see right now this is not, whatever this is not going to be 0. So not a factor. So the x plus 3 is not a factor. Let's try the 1/3. So I have 1, negative 1, negative 1/9, and 1/9. 1 drops, I get 1/3. This gives me negative 2/3. So I do this multiplication, and I end up with negative 2/9. So negative 1/9 and a negative 2/9 is negative 3/9. So this is going to give me negative 3/9. But negative 3/9 is the negative 1/3. So now this positive 1/3 and this negative 1/3 is negative 1/9. Ooh, so that is a factor. So that tells me that x minus 1/3 is a factor. And then my last one is positive 3. So 3, and then I have 1, negative 1, negative 1/9, and 1/9. 1 drops. This gives me 3. This is 2. This gives me 6. This gives me 5 and 8/9. I don't have to go any further to know this is not 0. So x minus 3 is not a factor. All right, one last one. I'm going to start with just putting 0 in there because it's there and it's nice. I put 0 in there, and by the way, this is going to give me not 0. So f of 0 is equal to 3, not equal to 0. So x is not a factor. I'm going to do 1. So I have 5 minus 8 plus 8 minus 8 plus 3. Well, this negative 8 and that positive 8 cancel. 5 and 3 is 8. Those all cancel. Oh, that one equals 0. So that tells me that x minus 1 is a factor. Now I'm going to do synthetic, because you can do a mix. Ball out of control. 5, negative 8, 8, negative 8, 3. 5 drops. This gives me negative 1. This is negative 9. This gives me 9/5. Let me see what this is. 8 plus 9/5. That would be 49/5. Yeah. And then I'm going to multiply that by a negative 8, negative 5. So that gives me a negative 49 over 25. Okay, so I'm going to add these two together. That gives me a negative 249 over 25. Well, that's a whole lot of fun. And then this gives me a positive 249 over 125. And this is not equal to 0. Okay. So notice the ones that were a 0 here, like 1, not interesting. The negative 3 and the positive 3 did not work, but the 1/3 did. Notice how 1/3 works, and it's a factor of this. Here the 1 works well. 1 is a factor of both 5 and 3. So let's take a look at the one up above. 3 is a factor. X minus 3 is a factor, I should say. And that is actually one of the factors here. That leads us to the rational zeros theorem, and it says the potential rational zeros, we're not guaranteed them, are going to be all of the factor choices of the constant and all of the factor choices of the coefficient, where the factors of the constant are going to be over all the possible factors of the coefficient. P is a factor of the constant, Q is the factor of the leading coefficient. These are the possible zeros. That doesn't mean they're guaranteed zeros. They're just possible zeros. So since it's going to be P divided by Q, I better figure out what P would be. P could be the factors of 12, which is our positive and negative 1 and 12, positive and negative 2 and 6, positive and negative 3 and 4. Q here is just positive and negative 1. So P divided by Q combinations are 1 over 1, 2 over 1, 3 over 1, 4 over 1, 6 over 1, 12 over 1. negative 1 over 1, negative 2 over 1, negative 3 over 1, negative 4 over 1, negative 6 over 1, and negative 12 over 1. Similarly, if I did negative 1 over a negative 1, that gives me a positive 1. So I can actually write this list, because I want to make this list shorter, is positive, negative 1, 2, 3, 4, 6, and 12. That is a ton of zeros, but those are all potential. I'm not guaranteed any of them will be zeros, but they are possible zeros. So now let's take a look at this example. My p, the factors of p, which is this, are positive, negative 1, and 2. Q is the 15, so positive and negative 1, 3, 5, and 15. So p divided by q is positive and negative. I have to do 1 divided by 1, 1 divided by 3, 1 divided by 5, 1 divided by 15, 2 divided by 1, 2 divided by 3, 2 divided by 5, and 2 divided by 15. So I have 1, 1/3, 1/5, 1/15. We have 2, 2/3. We have 2/5, and 2/15. These are just a possible. These are not, by the way, necessarily guaranteed to be the zeros. And let's take a look at my last example here. Let's do this one up here. P is 6, so I have positive, negative 1, 2, 3, and 6. Q is 10, so actually I'll make that a lowercase q, so it's not confused with the quotient. Is 10, so I have positive, negative 1, 2, 5, and 10. 1 divided by 1, 1 divided by 2, 1 divided by 5, 1 divided by 10, 2 divided by 1, 2 divided by 2, 2 divided by 5, 2 divided by 10, 3 divided by 1, 3 divided by 2, 3 divided by 5, 3 divided by 10, 6 divided by 1, 6 divided by 2, 6 divided by 5, and 6 divided by 10. So the possible zeros are 1, positive, negative 1, 1/2, 1/5, and 1/10. And we also have 2 over 1, which is 2, 2 over 2, which is 1, so I don't need to write that, 2 over 5. And 2 over 10 is 1/5, so 2 over 10 is 1/5, so I don't have to write it again. Then I have 3 over 1, so 3 over 1, which is 3, 3 over 2, 3 over 5, and 3 over 10. And we continue. I've got 6 over 1, 6 over 2, which is 3, so don't write that. I have 6 over 5, and then I have 6 over 10. Well, 6 over 10 reduces to 3 over 5, which I already have, so I don't have to write that one again. So those are all my potential zeros. So, suppose you found a potential zero of a polynomial function using a rational zeros theorem. Then you're either going to use synthetic division to check and numerical order to see if the zeros are actual zeros. You find a remainder that keeps getting larger. What does this mean? So say I go ahead and I think I'm going to use this very first example here. And I'm going to start with negative 12. So I'm going to put negative 12, and you can either do synthetic or you can do the factor remainder theorem. But if we do synthetic, let's see what happens. I'm going to have 1 in x to the 7th. I don't have an x to the 6th, so I better put in a 0. I have 37 for x to the 5th coefficient. I don't have an x to the 4th, so I better put in 0. I don't have an x to the 3rd, so I better put in 0. I'm going to put in negative 6 for the x squared. I don't have an x, so I better put in 0. And then I have 12. To count 7, 6, 5, 4, 3, 2, 1, and then the constant. Now, as I look at this, and I think, yeah, I'm probably not going to use synthetic division because negative 12 is fairly large-ish compared to like 1, 2, and 3. And there's a lot of missing terms. So I would suspect that putting it into synthetic division is not going to be a whole lot of fun. So let's just do, instead of doing synthetic, let's do f of negative 12. And in this case, way faster than synthetic division. And I get a super large negative number. So I have negative 4503944. That's pretty large. So that tells me I'm pretty far away from the x-axis if I'm getting such a large number. Let's try synthetic division because the 2 isn't going to be too bad, a negative 2. If I were to do this with negative 2, again, because of the number of terms for the synthetic, I probably would just put this into the function, but let's do synthetic. 1 drops, negative 2, and this gives me negative 2. This gives me 4. This gives me 41, and I'm going to stop right there. There is no way at this point, if I were to continue putting this negative 2 in here and adding it and then keep doing this, is this going to be 0 when I get done? Like, I'm just not going to get 0. So if I do negative 2 into the original function, you're going to follow me as I do this in my calculator. Negative 2 raised to the 7th plus 37 multiplied by negative 2 raised to the 5th. Minus 6, negative 2 squared, and then plus 12. I've got a larger number, magnitude-wise it's smaller. I'm closer to the x-axis. So I have 1,324, and it's a negative number. So I'm getting closer, right? So what I would do is say, okay, what happens if I put in 2? Where are we now? I ended up with a positive 1,300. Now, somebody had asked in class, why do we care about the intermediate value theorem? If I were to draw this on these points on the graph, and I'm obviously not going to draw this to scale. So I'm going to come out here to negative 12, and I have this negative 4503944. Here's my point. And I have a negative 2, and so here's negative 2, and I have this point, which is negative 1324. And then I put in a positive 2, and I end up with this, which is the 1,300. Somewhere between 2 and negative 2, because of my output values, between here and here, somewhere between these, I have to have a 0. Somewhere between these two, I have to have a 0. I have to. By the IVT, the intermediate value theorem, if f of A is positive and f of B is negative, or vice versa, I had to have changed. I had to have crossed the x-axis. Somewhere along there. And that's because I have to be able to go through these points smoothly without backtracking and doing weird stuff for a polynomial. So I have to have crossed. A being the left, B being the right. So by the intermediate value theorem, if one side is positive, one sign is positive and the other sign is negative, and it doesn't matter which one's which, you had to have crossed. So let's go back to this and say, okay, well, I skipped over negative 1 and 1. Let's see what happens if I go back to this problem. I'm just going to erase all of this. Spend some time on this problem, because you're all going to say, when do I know when to stop? So f of 1. When I put in 1, I'm going to get 1 plus 37, and I wrote 36. I have 1 plus 37 minus 6 plus 12. Now, this number, because it's going to be 38, it'll end up being 38 minus 6 plus 12 is 44. That's still positive, so I put in 1 and I'm down here at 44. I'm getting closer to the x-axis. Now let's try f of negative 1. I put in negative 1, I'm going to get negative 1, negative 37, positive, or still negative 6, and positive 12. This is going to be a negative number. So I have negative 38 minus 6 more plus 12 is negative 32. So somewhere between negative 1 and 1, I had to have crossed. I have no idea what this graph looks like, but I do know somewhere in there, I don't know where it's crossing. Don't assume that my picture is to scale and it's crossing at 0, because it's not. Somewhere in there, I know that I had to have crossed somewhere. Now, I don't know what the shape is, but I can tell you that it had to have crossed between there, because f of 1 is greater than 0, f of negative 1 is less than 0. By the IVT, I had to have crossed. And that's why I said that's kind of an important theorem. I know I kind of birdwalked. Okay. So, fundamental theorem of algebra states, if f of x is a polynomial where the degree is bigger than 0, so we're not talking about a constant, then f of x has at least one complex 0. We can use this theorem to argue that f of x of a polynomial of degree where it is not a constant and a is a non-zero real number, then f of x has exactly n linear factors. What this tells me is that I can take any polynomial, in theory, and factor it, and whatever the degree of that polynomial is how many factors I'm going to end up with. Some of them may be complex, some of them may not be complex. But if you remember, every real number is complex. I can take any real number, say the number 5. I can write it as complex by writing it as 5 plus 0i. So I can get a strictly real number, or I can get a complex number, but I am guaranteed to factor it into n number of factors, assuming, of course, that you may or may not have multiplicities that will bump up or make it look like you have less factors. But the multiplicities all match up, so you're going to have n number of factors. If we then mix that with a complex conjugate theorem, it says, according to the linear factorization theorem, a polynomial function will have the same number of factors as its degree, and each factor can be wrote in the form of x minus c, where c is a complex number. Remember, this is wrote as a complex number. If the polynomial function has real coefficients and a complex 0 in the form of a plus bi, then it must also have its complex conjugate as a 0, which is a minus bi. And that's because if I have real coefficients and I don't have any complex numbers to begin with, I can't multiply numbers together then unless they're complex conjugates to eliminate the complex number. So if you have 3 minus I as a 0, then what also has to be a 0 is 3 plus I. They have to go in pairs, complex conjugate pairs. So, the steps to find the linear factors of a polynomial. What we're going to do, let's see if I got anything with the Descartes on here. I don't have Descartes. Oh, I guess we better talk about Descartes before we do the steps of the polynomial. And it's not in here, but it's in the book. So let's talk about Descartes' rule of sign. Now, if you got nothing better to do, go research Descartes. He's a Frenchman. He was a mathematician. He was also a philosopher. With Descartes' rule of sign, it says, let me zoom in And I'm actually going to erase this so I can make it smaller so I can write all over in this place. All right, so Descartes' rule of sign says this. Descartes' suppose we have this polynomial f of x, which is equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 a sub 2 x squared plus a sub 1 x to the 1 plus a sub naught. The number of positive real roots or zeros is equal to the number of sign changes between the terms or that number minus 2, minus 4, minus 6. So let's call that number of sign changes S. So, or S minus 2, S minus 4, S minus 6, etc. Now, to find the negatives, we do f of negative x. You have to put negative into the original function, a negative x into the original function. And then the number of negative real zeros or roots is equal to the number of sign changes between the terms of f of negative x, or what do we want to call this? We don't want to call it n because that's the degree of the polynomial. We just use s, so let's use t minus 2, t minus 4, etc. So the first thing I like to do when I am trying to figure out the linear factorizations is to use the rational zeros theorem. To decide how many possible, or what our possible rational zeros are. The second thing I like to use is Descartes. And what that's going to do is tell me how many positives and how many negatives. And the reason I do that is because if I come up with no positives or no negatives, then that takes that rational zeros, the possible rational zeros that I found in step number 1, and eliminates half of them. The third thing I like to do is use the factor remainder theorem. Factor / remainder theorem until I find a zero. Once I find a zero, then I'm going to use synthetic division. To bring down the function to a quadratic. And then I factor that remaining quadratic. However you like to do it. With a quadratic formula or just regular factoring. Okay. So we're going to start with a P. This is the rational zeros theorem. P is 1, positive and negative 1, 2, 3, and 6. Q, so here's step number 1. Q is equal to positive and negative 1. So P divided by Q, the possibles are positive 1, 2, 3, and 6. That is 8 possible zeros. Now, I don't want to do that. The second thing I'm going to do is Descartes. So I'm going to come up here and I'm going to note how many times the sign changes. So positive to positive didn't change. Positive to negative, it changed once. Negative to negative, it did not change. So this tells me one positive real zero. So that means that just took and eliminate potential zeros, because once I find one positive one, I'm done. I'm not going to look for any more positive ones. Do f of negative x. I do f of negative x, and I have negative x to the third plus 3x squared becomes positive 2x minus 6. Here to here changed. Here to here did not, and here to here changed. So this tells me I have 2 or 0, because remember it comes down by a factor of 2, negative real zeros. One positive real zero and 2 negative real zeros. That's what Descartes does this. So now I'm going to use the factor remainder theorem. So the third step I'm going to do is the factor remainder theorem. So I'm going to do f of, I'm going to put in 1. I'm going to see if I can chase my positive real zero first. I put in 1, I get 1 plus 3 minus 2 minus 6. This gives me positive 4 minus 2 is positive 2 minus 6, so this is a negative 4. I'm going to try f of 2. Now remember, I'm also going to use the intermediate value theorem because of the fact if the sign changes between 1 and 2, I know I have a 0, but it's not a rational 0. So I'm going to have 8 plus 12 minus 4 minus 6. So I end up with a positive number. So 20 minus 10, so positive 10. I'm going to stop chasing at this moment. I'm going to stop chasing my positive because this output is negative, this output is positive. I had to have crossed somewhere between them. So I know where my positive 1 is. The positive 1 is in the interval between 1 and 2. But it's not a nice number. So let's start doing the negatives. Let's do f of negative 1. F of negative 1 is negative 1 minus or plus 3 plus 2 minus 6. Well, this is, let me see, that is negative, so positive 2 plus 2 is 4 minus 2, so negative 2. Let's do f of negative 2. So I'm going to get negative 8 plus 12 plus 4 minus 6. And this gives me, this is going to give me a positive 4. Well, this also tells me, since I went from negative to positive, I have a 0 in between here. So I have a 0 between negative 1 or negative 2 and negative 1. And these also change from negative to positive. So I must have a 0 in here between 1 and 2. But they're not rational zeros, so that doesn't help me. So let's do f of negative 3. And I put that in there, and I'm going to get negative 27 plus 27. Oh, this is looking good. Plus 6 minus 6 is equal to 0. I found my 1 0 that is negative, and it's rational. So now my next step, I'm going to come over here, and I'm going to do my next step. I'm going to do my synthetic. So I'm going to put in negative 3. And I only have to do 1, because if I do 1 synthetic, this is going to bring it down to a quadratic. So my coefficient on the x cubed term, which is 1, the coefficient on the squared term, which is 3, the coefficient on the linear, which is -2, and then 6, -6. -1 drops, this is -3, this gives me 0. -3 and 0 is 0. This gives me -2. And I have here +6 and 0. So my quadratic I'm left with is x squared minus 2. There's no way I would have found that by doing all of this stuff here. So this tells me I have x is equal to positive and negative square root of 2. So my linear factorization is x plus 3, and that comes from here, x minus the square root of 2, and x plus the square root of 2. Yay! All right. So if I were to graph this, I have to do the x or the y-intercept of -6, so 2, 4, 6. I'll put it right here. It is by factors of 2, so this is -6. I have the square root of 2, which is more than 1 less than 2, so I'm going to put right there the square root of 2. And right here, the negative square root of 2, and -3, which is right here. Leading coefficient's positive, and so it's going to look something like this. And there is my graph, and there is the factoring. All right, let's do one more. I'm going to let you all do that one. I'm going to do this one. And the reason I'm going to do this one is because I'm going to have to do synthetic division more than once. Once you find a 0 here, you only have to do synthetic division once. I am going to give you the answer, though. So this f of x, factored in its linear factorizations, are going to be x minus the square root of 3 over 2, x plus the square root of 3 over 2, and then x minus 1. First, on this one I'm going to list out my possible zeros. So my possible zeros is p is going to give me positive and negative 1, 2, 5, and 10. Q is going to give me positive and negative 1. So my P divided by my Q are positive and negative 1, 2, 5, and 10. Now I'm going to use Descartes. This does not change. Here's 1. Here's another one. And here's another one. So I'm going to have 3 or 1 positive real 0. Because remember, they go down by 2. Now I'm going to do f of negative x. This becomes x to the 4th still. Then minus 5x to the 3rd. Minus 27x squared. Minus 31x minus 10. Ooh, that's nice. It changed one time. So that tells me I have one, I'm guaranteed one negative real 0. So I'm going to start with the negatives first. So now I'm going to use the factor remainder theorem. I'm going to do f of negative 1. I always start around the origin because my life is easier when I start around the origin. So this will become 1 minus 5 plus 27 minus 31 minus 10. And I get negative 18. Okay, let's try f of negative 2. F of negative 2 is going to be a positive 16. It's going to be a minus of 40. It's going to be minus, I don't know what 27 times 4. I don't know what that is. Not off the top of my head. Times 4. It's 108. So minus 108. And then minus 61 minus 10. Well, I can tell you that that's not going to be 0. This is a negative 204. I'm moving quite a ways from the y or the x-axis. Putting in a negative 5 or a negative 10, my outputs are not going to be any closer to the x-axis. So let's try a positive 1. So f of 1 is equal to 1 plus 5 minus 27 plus 31 minus 10. And I get 0. Ooh, this tells me that x minus 1 is a factor. Now I can do synthetic division now, but this is only to bring it down to a cubed. Let's see if I can find another one. Let's do f of 2. So this is 2 to the 4th plus 5 multiplied by 2 to the 3rd minus 27 multiplied by 2 plus 31 that's 27 multiplied by 2 squared. 31 multiplied by 2 and then minus 10. Get my calculator out. Ooh, this also equals 0. So this tells me that x minus 2 is a factor. Okay, so now I'm going to come over here and do my synthetic division. I'm going to start with 1, and I need my coefficients, which are 1, 5, negative 27, 31, and negative 10. 1 drops, 1 goes up, we get 6. 6 goes up, negative 21, negative 21 goes up, positive 10, and 0. Now, what this is x to the 3rd plus 6x squared minus 21x plus 10. I am, however, going to do synthetic division again, but with my 2, and I'm just going to do it right there. I'm just going to keep bringing this down. 1 drops, 2, this gives me 8, 16, it gives me negative 5, this gives me negative 10, and 0. Where I am now is that this is x squared plus 8x minus 5. That comes from here. I had the x minus 1 and I had the x minus 2. That comes from here and here. I'm not done. I have to factor this. Now, this does not factor nicely, so I'm going to have to throw it in the quadratic. So x is equal to negative b, so negative 8 plus or minus the square root of b squared, so 8 squared, minus 4, a is 1, c is negative 5, all over 2a. So I get negative 8 plus and minus the square root of 84 over 2. But the 84 is a perfect square embedded in there. That's 4 multiplied by 21. So this is negative 8 plus and minus 2 the square root of 21 over 2, which is equal to negative 4 plus and minus the square root of 21. All right, my linear factorization now is x minus negative 4 plus the square root of 21, x minus the negative 4 minus the square root of 21, and I had x minus 1 and I had x minus 2. And that is my linear factorization in all of its glory. That was some good times. Here's some questions to ponder. Suppose you found a potential zero of a polynomial function using rational zeros theorem. Then using synthetic division to check in numerical order, you see that the potential zeros are actual zeros. You find the remainder keeps getting larger. What does this mean for the remaining zeros? So we talked about this. As I go through sequentially, and I start at 0, and I go left, and I go right from 0. And I stopped up here when I got to negative 2, and I was moving away from negative 18 to negative 200. These are the y values. It is likely that my negative 5 would have produced an even smaller number. It would have been, magnitude-wise would have been large, but it would have been an even smaller number. And the same thing with negative 10, so I just stopped. And so that's what it's telling you is when you go through that and your remainders keep getting larger, or in my case was smaller, then it's probably not going to have a zero out there. What is the difference between a rational and real zero? Well, all rational numbers are real, but not all real numbers are rational. So a rational number is something that we can write as a fraction or a truncated decimal, so like 3/5. That's an irrational. A real zero is the square root of 2. I can't write that as a fraction. So in some of these, I ended up, like this first one, I ended up with the square root of 2. And this one, I also ended up with some real numbers. They just weren't rationals, which is why they weren't showing up on the rational zeros theorem. Which then has you to ponder, why does the rational zero theorem not guaranteed finding all the zeros of the polynomial function? Well, that's because sometimes, even though I may not see a square root of 2 as a coefficient, it could definitely show up as a factor. So this rational zeros theorem just gives us possible rational zeros to check. It doesn't give us the actual. Now let's take a look at this example. I have the complex numbers, and I have some real numbers, I have some degrees, and I have some information about the behavior. If you remember from before, if I have one complex number by default, I always have its conjugate. So what I have is x minus 2i, we have x plus 2i, and then we have x minus 1. Now let's look at the behavior of the graph. So first of all, let's count. We have 1, 2, 3, degree 3. We have 3 factors. Cool. As x goes to negative infinity, I go down. As x goes to positive infinity, I go up. That means we're going to assume that our leading coefficient is positive 1 or negative 1, simply because I don't know anything more about it. Like I don't have another additional value to check to actually find what my leading coefficient is. So I'm going to assume my leading coefficient is a positive 1. Let's take a look at this one. We have x minus 3, or 1 minus square root of 3. That means I have 1 plus the square root of 3 because I have rational real zeros. That means here I must have 1 minus 3i, which means 1 minus 3i must also be a factor. So I have x minus a 1 minus square root of 3. I have an x minus a 1 plus the square root of 3. Oh, I have an x. This one produces just x, so I'll put that out front. And then I have x minus 1 minus 3i. And then I have x minus 1 plus 3i. I'm just going to check to make sure I have the appropriate factors. 1, 2, 3, 4, 5. Degree 5. Cool. This is telling me as x goes to negative infinity, my function goes up. As x goes to positive infinity, my function goes down. My leading coefficient must be a negative 1. So take a look at this last one. I have to have a complex conjugate here, complex conjugate here, and I have to have a negative square root of 3 here. So my factors are x minus 1 plus 2i. I must also have x minus a 1 minus 2i. I have x minus 1 minus 3i. That means I must also have an x minus 1 plus 3i. I have an x minus the square root of 3. And I also must have x plus the square root of 3. Let's count to make sure I have the appropriate numbers. I have 1, 2, 3, 4, 5, and moving this over, 6. Cool. This tells me as x goes to negative infinity, I go up. As x goes to positive infinity, I go up. So I must have a leading coefficient of positive 1. And here are some applications of what we have. So let's start with the first one. The length, width, and height are 3 consecutive whole numbers. So let x be the first number. X plus 1 is the second number. X plus 2 is the third number. That means x multiplied by x plus 1 multiplied by x plus 2 is equal to the volume, which is 120. So what we have to do, and we're going to be so excited about this, is we are going to have to multiply all of this through, bring the 120 to the other side of the equal sign, so we set it equal to 0, and then refactor it. All right, so I'm going to multiply the left-hand side. I'm going to get x cubed plus 3x squared plus 2x, and then bring that 120 to the other side, so minus 120 is equal to 0. Now, I'm going to have to figure out what the possible zeros are. So P is going to be a lot of things. 1, 2, 3, blah, 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 all the way down to 120. Q is going to be just 1. All right. So that's my first step. My second step, using Descartes' rule of sign, as I only have one sign change. And so I have one value for x. So 1 positive, real 0. And then I do f of negative x, and I'm going to get negative x cubed plus 3x squared minus 2x minus 120. Here's one sign change. Here's another. So I'm going to have 2 or 0. I can tell you that if I have a 0, I can go ahead and just toss it, simply because I have 3 consecutive whole numbers. It's in what it says, which means that even if I get a negative number, I have to toss that because I'm looking for whole numbers. So I'm really just focusing in on the first one. So I'm going to do f of, let's just start with 3 and see where we are. So I'm going to have 3 squared plus 3 multiplied by 3 cubed, I should say, multiplied by 3 squared plus 2 multiplied by 3 minus 120. Now this is going to give me a negative number, but let's see how close we are. Or yeah, we're a negative number, but let's see how close we are to the x-axis. I got negative 60. I'm going to do f of 4 and see where I'm at. 4 to the third plus 4 multiplied by 4 squared plus 2 multiplied by 4 minus 120. And I get 0. So I actually don't have to do anything more. Why don't I have to do anything more? Because if x is equal to 4, x plus 1 is equal to 5, and x plus 2 is equal to 6. 4 multiplied by 5 is 20, multiplied by 6 is 120, so I'm done at that point. I actually don't even have to factor it. So the length is 3 inches more than the width. So the length is the width plus 3. The width is 2 inches more than the height. And the volume is 120 cubic centimeters. All right. So now I want to write this all in terms of the height. I have length multiplied by width multiplied by height. If the length is the width plus 3, but the width is h plus 2, so it's h plus 2 plus 3, so my length is h plus 5. My width is h plus 2, and my height is h, and this gives me 120. Same thing as I did before, is I need to go ahead and multiply the h's through, so I'm going to have h cubed plus 7h squared plus 10h, subtracting off the 120 is equal to 0. And I'm going to let you finish that one, not only because I am a giver that way, but also because we are at 1 hour and 4 minutes, and you all have hung in there that long, and I appreciate. You're going to follow the same algorithm as I did above to find the answers. I'll give you the answers, though. If you did all your steps correctly, you should have h is equal to 3. The width is the height, which is 3 plus 2, so 5. And the length, which was the width of 5 plus 3, which is 8. And 3 multiplied by 5 multiplied by 8 should give you 120. And those are your 2 applications of polynomials. We will see you in class, and thanks for hanging out.